Welcome to Inspire the Vision. Today we're diving deep into the world of underwater tunnel construction, a realm where engineering meets the impossible. Imagine driving beneath a river or an ocean, knowing that millions of gallons of water rest just above your head. It feels like something out of a science fiction story, but it's very real. How are these tunnels built? How do they withstand the immense pressure, the shifting earth, and the constant threat of water intrusion? It's a marvel of human ingenuity, and today we'll uncover the step-by-step process of building underwater tunnels, exploring the challenges, the techniques, and some of the most famous examples from around the world. So let's talk about how these incredible structures come to life. Before a single shovel breaks ground, the first step in tunnel construction is meticulous planning. This is not a project where you can afford to wing it. Engineers, geologists, and architects work together to study the proposed site. They analyze the seabed or riverbed where the tunnel will be built, conducting geological surveys to understand the type of soil or rock they'll be digging through. Will they encounter soft clay, hard granite, or a mix of materials? Each type presents unique challenges and requires different methods of excavation. But that's just the beginning. Engineers also have to consider the depth of the water and the immense pressure it exerts. The deeper the tunnel, the greater the pressure. Imagine being hundreds of feet below the surface with the crushing weight of the ocean above. The tunnel must be strong enough to withstand that pressure without buckling or cracking. Then there are natural risks like earthquakes, tidal forces, or shifting sediments to consider. Every single variable must be taken into account because mistakes at this stage could lead to catastrophic failure later on. Once the planning phase is complete, the real work begins. One of the most common techniques for building underwater tunnels is the Immersed Tube Method. This method involves constructing massive sections of the tunnel on land. These sections, called tubes, are made from reinforced concrete and steel, designed to be watertight. Each tube is hollow inside, allowing space for traffic, whether it's cars, trains, or even utilities. Once they're completed, the tubes are sealed to keep water out, floated to the construction site, and carefully lowered into a trench that has been dredged into the seabed. Let's take the Hampton Roads Tunnel in Virginia as an example. This tunnel connects two cities beneath the water and was constructed using the Immersed Tube Method. Each massive tube section was floated into place, aligned perfectly with the others, and then sunk into a pre-dug trench on the riverbed. Cranes and precision tools ensured that each section fit together seamlessly. Once all the sections were in place, engineers pumped out the water from inside the tunnel, creating a dry, safe passageway for vehicles. It's like assembling a giant underwater puzzle, piece by piece. For deeper tunnels, where the Immersed Tube Method isn't practical, engineers turn to the tunnel boring machine TBM. TBMs are among the most impressive machines ever built. Imagine a massive cylinder as long as a football field with a rotating cutter at the front. This cutter grinds through soil, rock, and sediment as it moves forward. Behind the cutting head, the machine installs precast concrete segments that form the tunnel's walls, creating a waterproof shell as it progresses. One of the most famous examples of TBM use is the Channel Tunnel, or Chunnel, which connects the UK and France beneath the English Channel. TBMs dug through miles of chalk and clay, with machines working simultaneously from both the British and French sides. They met in the middle with pinpoint accuracy, creating a high-speed rail link that revolutionized travel between the two countries. The precision needed to align these two halves of the tunnel perfectly, miles under the sea, is truly astonishing. Another technique often used is the cut and cover method, typically for tunnels that aren't too deep. In this method, engineers excavate a trench on the seabed or riverbed. The tunnel is constructed inside that trench, either as one continuous structure or in sections. Once the tunnel is complete, the trench is filled back in with soil and sediment, restoring the seabed to its natural state. This technique is simpler and less expensive than others, but is only suitable for shallow waters. Regardless of the method, one of the most critical aspects of underwater tunnel construction is waterproofing. Imagine the catastrophic consequences if water were to seep into the tunnel. Engineers use multiple layers of protection to ensure the tunnel remains dry. Reinforced concrete, steel linings, waterproof membranes, and specialized rubber gaskets are all part of the waterproofing system. Every joint between tunnel sections is meticulously checked and sealed, because even the smallest crack could let water in, leading to potential disaster. Another major challenge is ventilation. In a tunnel, especially one used by vehicles, air quality can deteriorate quickly due to exhaust fumes and heat. Without proper ventilation, the air inside could become toxic. Modern tunnels are equipped with sophisticated ventilation systems that use massive fans to circulate fresh air. Sensors monitor air quality in real time, ensuring a safe environment for travelers. The Tokyo Bayako line in Japan is a great example of this. Stretching nearly 6 miles across Tokyo Bay, this tunnel and bridge hybrid features an advanced ventilation system that keeps the air clean and comfortable. Let's talk about another fascinating challenge: the earthquakes. In areas prone to seismic activity, tunnels must be designed to flex and move without breaking. The Eurasia Tunnel in Istanbul is a perfect example. This tunnel crosses beneath the Bosporus Strait, connecting the European and Asian sides of the city. It was built with special flexible joints that allow it to withstand the tremors of an earthquake, ensuring the tunnel remains intact and travelers stay safe. Environmental considerations are also crucial. Building underwater tunnels can disrupt marine ecosystems, so engineers work closely with environmental experts to minimize their impact. They carefully plan dredging and construction activities to avoid harming marine life, and often restore the seabed to its original state after construction is complete. Balancing human progress with environmental responsibility is a vital part of any large-scale engineering project. Once construction is finished, these tunnels aren't just functional, they're symbols of human achievement. They represent years of planning, hard work, and technological innovation. They connect cities, countries, and even continents, making travel faster and more efficient. But more than that, they show what humanity is capable of when we dare to push the boundaries of what's possible. Take the Seikan Tunnel in Japan, the world's longest underwater tunnel, as an example. Stretching over 33 miles, it connects the islands of Honshu and Hokkaido beneath the Tsugaru Strait. It's a testament to the determination and ingenuity of engineers who refuse to let nature's obstacles stand in their way. Thank you for joining us on this journey into the depths of underwater tunnel construction. If you found this exploration fascinating, be sure to like the video and subscribe to inspire the vision for more incredible stories of human achievement. Until next time, keep dreaming big, and remember the future is built by those who dare to dig deep.